Hello. In our discussion related to motion in a plane, we are going to start off this new series, which is circular motion. Now, the circular motion is also motion that is constrained to a plane. So, this is part of the motion in a plane series. And the circular motion is, as I said, is constrained to a plane where obviously we are considering two-dimensional cases, either the xy axis or the yz axis or zx axis, zx planes, sorry, xy, yz and zx planes, or any plane uh, which is probably parallel to any of these, or may not be parallel, but it's still uh, in some frame or the other it will be constrained to two axes, not the three-dimensional one. The three-dimensional will be a spherical motion, so obviously we are uh, again, as I say, we are constrained to a two-dimensional system. So this, as an object travels, let me take the point, initiating point as A, and suppose it is traveling counterclockwise in this direction along this line, and it's moving along a circular path like that, and it has a certain radius, r. As it moves from the point A to B, it sweeps through an angle theta with respect to the center of the circle, let that be at O. So along that plane, an object moves from the point A towards the point B, and in the process it sweeps through an angle theta. The angle theta there is termed as the angular displacement. Now, displacement, as we have studied already, that displacement is the shortest distance from the initial to the final point. Here, the displacement is also the shortest part, but the shortest form here being the angle. And so the units in this case will be degrees or radians. Popularly, we take it as radians. And as you know, radians and steradians, in case of solid angles in three dimension, they are supplementary units. They do not possess any dimension. So this thing over here, the angle, that does not possess any dimension, but definitely some unit in terms of radians or degrees. We usually use the radian part. So as with an angular displacement, it must have taken some time, obviously, to travel from the point A to B, and that angular displacement over time, remember, the linear displacement over time was giving us the velocity. Here we have the term called as angular velocity. Angular velocity, in scalar terms, it will be angular speed. Now, this angular velocity obviously is related to the angular displacement as angular displacement per unit time, or the angle swept per unit time. So its unit is in radians per second. And if we were to relate it with the distance that the particle has covered, the distance obviously is the arc length AB that it has covered. Now, the arc length AB, as we know from the formulas that we have studied in our school at a school level, so AB, the arc, is equal to some angle, the angle swept, obviously, that is theta, multiplied with the radius, so r times of theta. Now, with AB, as we know, it is obviously the distance, in this case s, right? And distance by time was giving me the speed, and so if I have divided the distance with time, so I can do the same thing on the right hand side, that is, distance here AB is equal to r times of theta in this case, and that divided by time. Now theta divided by time obviously was omega, that is, it's omega as in capital omega, small omega. The capital omega is in ohms, that is the symbol used for resistance. So this is omega, and we should not read it as W. So this is theta by T, which is omega times R. Now this, as you know, is speed, and it's in scalar form. What about the vector part of it? Obviously, because we are dealing with angular displacement and angular velocity, we must give it a vector form. Now vectorially, we have V to be equal to omega cross R. This is the vector form. That means in this case, if omega, that is the angular velocity, if it is acting out of the plane, then out of the plane that we are seeing right now, so in that case the radius vector that acts outwardly from the origin towards the particle, because the radius vector here gives me the position of the particle with respect to the origin. So with omega pointing outward, crossed with r, omega cross r, here using the right hand thumb rule, the velocity vector, that is the linear velocity, obviously is along this direction, which is correct as per our as per the picture that we have drawn in this case, because v will act tangentially. The velocity keeps on changing even though the person takes the same amount of sweeps through the same angle in the same amount of time, even if he maintains his speed, but the direction keeps on changing at every point, and that is why the velocity keeps on changing. At any instant, at any given point, the velocity obviously is directed tangentially, as I have shown in that figure. The velocity, being a vector quantity, is directed tangentially when omega is acted outward, that is the angular velocity is acting out of the plane, and r is directed towards the object. Now out of the plane, as I have drawn a circle at the point B representing out of the plane, dot and circle gives me out of the plane. If you are unaware of the right hand thumb rule and the vector product rule, then I would suggest you go through the vector playlist. Towards the end, I have discussed about the product of two vectors, and that is exactly what I have done over here. So the velocity is related to the angular velocity in this way, and obviously it has a dimension now, the velocity or the speed, uh, angular speed or angular velocity omega, because it is theta by t, so theta being dimensionless, that is just left out, so this is just t inverse. Now remember, t inverse is the dimension for frequency as well. It is the rate at which the cycle is maintained in a circular motion, and that is why omega is also known as angular frequency. So there shouldn't be any confusion with that, because it has the same dimension as frequency, obviously. So we relate the angular velocity, or we even term it as angular frequency. Now with the angular displacement and the angular velocities expressed, we can of course obtain the or give the expression for the instantaneous angular velocity. So the instantaneous angular velocity or the angular speed can be related as limiting del t to 0. We have del theta over del t, and that is equal to the derivative of the angle with respect to time. This is the instantaneous angular velocity. This is just the kinematics form that we have already discussed in linear case. This is the angular part of it. Now in case of acceleration of the system, it is the rate of change of angular velocity, and the acceleration in this case is represented by The angular acceleration in this case is represented by the symbol alpha. Alpha being the angular acceleration is equal to simply the change in angular velocity to the change in with respect to the change in time or the time interval taken for that change. Now this I'm writing in a modulus. You'll know why, because we are concerned about the scalar form of it first. So omega, as you know, is simply v by r, right? So we have this to be as v by r and instead of omega, so that is del v by r. R is constant, r does not change, and divided by del t. So del v by del t is simply linear acceleration. So this is linear acceleration by the radius. So linear acceleration is related to the angular acceleration as the radius times of the angular acceleration alpha. Let me rewrite that for you clearly. Now this, as v is equal to r omega a is equal to r times of alpha. A here is the linear acceleration and alpha is the angular acceleration. Now the linear acceleration with relation to the angular acceleration, having obtained that, we can go for the vector form of it. Now vectorially, if you remember, we have just discussed over here v is equal to omega times of r. So the rate of change of velocity is going to give us the linear acceleration, because that's linear velocity, and with the relation that we have obtained above, we have omega cross r instead of v. Now without breaking the order, because in cross product the order has to be maintained, so we have a d omega by dt crossed with r. Now this is the derivative rule where you put one of the things as constant and the other is differentiated. So we keep the first term constant in the next term and then crossed with dr by dt. Now if you observe closely, we haven't changed the order. Omega remains first, r remains later, omega remains first, r remains later, because this is the order that we have over here. So d omega by dt, as you know, we have just discussed that that is acceleration, angular acceleration. This is the instantaneous angular acceleration, and this is crossed with r, plus omega times of or crossed with dr by dt. Now that is going to give me velocity, but velocity in what form? Velocity in radial form. Now see, it may so happen that, suppose the radius here, the radius is constant, so dr by dt must be 0, one may argue. But consider the case where a particle is traveling along a curved path. Now in that case, as it travels along a curved path, let me just draw that in the next page for you. As a particle travels along a curved route like this. Now in this case, if it is moving from this place to this place, what happens is that this is a part of a circle. Maybe it's just an example that I am giving to you at this point of time. A straight line can be treated as a curved path as well. We'll be knowing that shortly. And this is a part of another circle. So in that case, the radius does change, and with the radius changing, here the radius is probably r1, here probably r2, and somewhere here, if you can take this segment over here that you consider, this can be a part of a huge sphere, because a straight line is a part of huge circle. Sorry, the straight line is just a small segment of a bigger circle. So in those cases, with the radius changing, you have a rate of change of position, and that is going to give us the velocity. Now going back to the figure in the previous page, if we have the velocity to be directed along this line over here, and the omega, as you remember, is going out of the plane, which is represented by that dot encircled. Omega cross v, if you use the right hand thumb rule, it is you curl your forefingers of the right hand from the omega vector, which is outward towards your face or out of the plane over here, and you curl them towards the velocity vector, which is acting tangentially, and you extend the thumb. If you extend it and you're doing it correctly, obviously the thumb is extended towards the center of the circular path, which is along the radius. So this term over here, omega cross v, is the radial term of the acceleration. This is the radial acceleration. A subscript r is the radial acceleration, plus alpha cross r. Now remember, acceleration is always taking place along the change in the velocity, along the direction of the change in velocity. Now here the angular velocity was acting outward, and the radius vector, if you see, is acting towards the object. So again we apply that cross product. So we again extend the forefingers out of the plane for alpha, which is acting towards the angular speed as well, angular velocity, and we take it, or we curl the forefingers palm side along the direction of r. So as we curl it, then the thumb extended from the right hand gives me the tangential direction, that is the direction of the velocity. And if you are obtaining a tangential term, obviously this is the tangential part of the acceleration. So the linear acceleration is actually, in case of a circular motion, the linear acceleration in this case is the sum of, or the vector sum of, the radial as well as the tangential acceleration. This is the tangential acceleration. So let me write it here for you. AT is the tangential acceleration, and AR is the radial acceleration, and the radial and tangential accelerations add up vectorially to give us the linear acceleration in case of an object moving along a circular path. Now there are some other terms that we can discuss as of now. We have the, let's just ignore the figure that we had drawn. We'll be using this left side of the space. The the time period, as you know, is the time that a particle which is moving along the circular track takes to complete one circular path. So this is the circular path that the particle is taking, and that one circle that it completes, it takes a certain time for it. Usually this is for uniform circular motion. So this time period is the time taken for that one complete cycle that the object takes. And how often does it take in a given unit of time, that is supposedly 1 second? So the number of cycles or circles that it completes per unit time is going to give me the frequency, usually represented by the symbol nu, and nu, or even f in simple terms. Frequency is the number of cycles. Now obviously number of cycles is just a number that it is completing, supposedly 2 cycles in 1 second. So 2 is just a number, but the time that is divided, that is the uh, that has a unit, and the unit is seconds. So the frequency, the time period is obviously the time taken, so it is, the unit is seconds, and in this case the unit is second inverse. So what we have over here is that the frequency is just the reciprocal of the time period. The frequency is second inverse, or even it is also called as hertz, named after the scientist. So the frequency is the reciprocal of the time period, and that essentially is the relation between them. As I had mentioned about the angular frequency omega, that is the angular speed, is the distance or the angular displacement that it covers in a given amount of time, and in one time period obviously the angle covered, it will be 2 pi radians, because it completes one full cycle. So that being the angular displacement in the given time, that is the time period, the whole time period. So 1 by time period being frequency, we simply have it to be 2 pi times of f. So omega is related to the frequency in this way, that omega is equal to 2 pi times of the frequency. As you can see, that it is directly proportional to the frequency, so that is why it's also termed as angular frequency. With these basics done and dusted, let's just move over to some derivation of centripetal acceleration. Now, in case of uniform circular motion, if we have an object to be moving along a circular path at a constant speed, remember I said that even if the speed remains constant, the direction keeps on changing, and with the change in direction the velocity changes, and because the velocity changes we have a scope for acceleration. So that acceleration leads to what we call as centripetal acceleration, and so let me just draw it one more time for you. So this is the radius of the circular path in which the object moves, and suppose it moves along this line. The circle may not be a perfect one, but I've tried more or less a circle, and suppose it again moves from one point A to the other point B. Now if you see that at the point A the velocity, let me just draw it with another ink for your better understanding. Use a green one this time. So this is supposedly the velocity over here. This is v1, and v2 is the velocity that it acquires as it moves to the point B. And with v1 and v2 are equal in magnitude, as we know, because it is moving with a constant speed, and that be equal to v. Let us suppose say that that is equal to v. Now with the velocities available to us, what we can move over to is that we consider another figure. We just draw the position vector with respect to the center for the as it reaches v2, as it reaches the point B, and in the process suppose it has swept through an angle del theta. Now if we produce this thing backward, that is v2 is produced backward, it meets v1 at a point. This is v1 and this is v2, and they meet at a point over there. This point, I'm magnifying the view for you, v2 over here, v1 moves from the point A and they meet somewhere. v2, remember, is produced backward. v2 from the point B V1 from the point A, and they are produced backward, and here we have the center where it has swept through an angle del theta, and this is the radius r. Seems good. Now with this feature available to us, or this diagram available to us, what we have over here is that this is tangential, so this is 90 degrees, this is 90 degrees, this is theta. This being a quadrilateral, this angle over here must be equal to 180 minus del theta, and what that leaves us with is that this angle over here, that has to be equal to theta, or del theta, suppose del theta, because this angle over here is 180 minus del theta. Remember, for a quadrilateral in this case, we have this angle, this angle, this angle, and this angle. All the four angles add up to 360 degrees, and with all the angles adding up to 360 degrees, two angles 90 and 90 go to 180. What is left is 180. Out of that, this is del theta, and from del theta we have this to be 180 minus theta minus del theta, and that leaves us, because this is a straight line, as you know, V1 direction extended, that is a straight line, and from that straight line we have an angle 180 minus del theta, and the other angle obviously is simply del theta. So that leaves us that V1 and V2, this is V2 and this is V1, and the angle between them is del theta. Now if we see this as del V, what we get is that, sorry, as it is moving from V1 to V2, so del V is the change in velocity from V1 to V2. So from triangle law, as you can see, V1 plus del V is equal to V2. So that means we have V2 minus V1 to be equal to del V, which is completely correct as in case of the change in velocity, and that change in velocity occurs over a given interval of time, so obviously it is del t, and that is going to give us the centripetal acceleration, because the acceleration is the rate of change of velocity with respect to time. Now we have to just obtain an expression for that. How do we do that? If you remember, we have V1 and V2 to be of equal magnitude, that is V. We just wrote it over here in that faint green ink that I used. And considering this figure, or even this figure, we have a similarity to consider. Now with del t obviously being very small, this thing that we have over here, this triangle OAB, that can be treated as a triangle instead of a sector. So that triangle is similar to this triangle. How is that? Because the angles over here are same, obviously with the angle same and the triangle having a total angle of 180 degrees, with the radius being the same in this case, and with V1 and V2 having the same magnitude in this case, these two angles must be equal, and that is why we have a similarity of two triangles, that is triangle OAB must be similar. Let me name this triangle. This triangle is something X, Y, and Z. Let me just name that randomly. So triangle OAB is similar to the triangle XYZ. With that similarity available to us, what we have is that the ratio of the sides must be equal So with the sides considered, the V1 side, which has the magnitude V1 divided by um, the side corresponding to that, is OA in this case of the OAB triangle. V1 by OA is equal to uh, let us say del V, which is the XY side, divided by AB. AB is the arc length, which is near more or less a straight line. So with this similarity available to us, let me use the other page for you. V1 mod is simply equal to, I'll be using this space that is there. V1 is simply equal to V, and OA is here equal to R, and that is equal to del V. What is del V? Del V is the change in velocity, and the change in velocity obviously occurs with the with okay, the change in velocity is del V. And what is AB? AB is the distance that it covers in time del t. So what is the distance in time del t? Distance is equal to speed uh, multiplied with time. So speed here is v, which is the magnitude of course, and time is del t. Now we have a del v by del t term over here, if you see, and del v by del t is simply the centripetal acceleration, the modulus of it. The v can get cross multiplied and get multiplied to the other v, so this is v square divided by r. So v square by r is the expression for centripetal acceleration. With the expression for centripetal acceleration available to us, we will be discussing about the direction of the centripetal acceleration. Let me give you a hint. It is directed towards the center. How? We'll be discussing that in the next video. Till then, thank you for watching.